Okay, ladies and gentlemen, today I'm going to have you do some more practice with centripetal forces and figuring out how the variables affect one another. Um, the formulas are your guides for doing that. So um, here's the centripetal force equation. So you can see from this that the force will be directly proportional to the mass. The force will be directly proportional to the velocity squared, so this will be a parabolic relationship. And the force will be inversely proportional to the radius. Similarly, you can use the same approach when you're dealing with the centripetal acceleration by using this formula. Then keep in mind as well that when we have things that are moving in a circle, then they have a linear speed with respect to their path around the circle, which is called their tangential velocity, and that's what's inside of this area right here, kind of beneath the griffin. The S stands for the arc length, which is kind of a strange notation, but tangential velocity is how far it is around a circle divided by the time it takes to go all the way around the circle. Because if you remember, this capital T was period, the time for a complete cycle. So 2 pi r would be a complete circle. So that makes sense. Then this form of it says that this is a frequency one, so we don't have to worry too much about this one at this point. But and tangential velocity is just the distance around the circle divided by the time it took. Or if you have multiple rotations, if you have 4 times around the circle, and you know the time it took, then you're going to be able to make sure that you have this as a factor of 4 divided by the time. So anyhow, mostly we're paying attention though to this formula right here. The centripetal force is mass times velocity squared over the radius squared. However, this force doesn't ever appear on a force diagram. The centripetal force gives you a direction and it gives you information about the magnitude of the force, but it's not an actual force on a force diagram. So that's a little bit of what I'm going to go through real quick right now. Let's touch on Newton's laws real quickly and how they fit in here. Newton's first law is really helpful in figuring out what force might be causing the centripetal acceleration and force. And that's by remembering that objects will move in straight lines unless there's a net force acting on them. So in the example of this won't ever move if there's no force on it, and this one won't ever stop, but they're moving in a line. If something is moving in a circle, then there has to be a net force toward the center of rotation. And to identify that force, you need to ask yourself this question: what's keeping this object in a circular path, or what's making it curve? If you have trouble figuring that out, then ask yourself, what would it do? What would have to happen for this thing to move in a straight line? What would have to disappear? So those are some of the kind of questions you can ask yourself to identify what the actual force is that is that is creating the centripetal acceleration and force. Okay, so the second law is clearly force equals mass times acceleration, and the centripetal force acceleration is a subset of that because it is F equals ma, but we simply take out the generic a and we put in the centripetal acceleration, which is v squared over r, and that's how we get centripetal force equals mass times v squared over r. So centripetal force equation is actually just a form of the second law. In some cases, we'll use the third law because we have action-reaction forces that can help us figure out what we might need to be using. Like, for example, here we have a contact with a wall. And so there's 2 forces here that could inform us about motion. This is not circulation, but it's just the only picture I could find. It was a third law picture. And then the last one, and that's not really a fourth law, but it's called Newton's law of gravitation. We covered this in 9th grade physics. And Newton's law of universal gravitation says that 2 objects with mass are attracted to one another in a manner that is directly proportional to the product of their masses and inversely proportional to the square of the radial distance between their centers of mass. So that's this picture and that's this formula. Lots of words, and we have to get used to being pretty sophisticated with those words so that we're going to be moving toward using more sophistication in the way we express what we're talking about. So be thinking about that as you do this assignment as well. So this is just a form of F equals ma, because on Earth, if we take if this small m is u and this large m is the mass of the Earth, then this value right here, this g, which is the universal gravitation constant, times the mass of the Earth, divided by the radius of the Earth's sphere, that is 9.8 meters per second squared. That's what you get if you put these values together. So this is the same equation you've been seeing all along, that force due to gravity is mass times the acceleration of gravity of the gravitational field. But these values right in here that I'm circling with the cursor, those are the ones that help you get that magical value of the gravitational field. So from this, you can kind of see that gravitational fields diminish with distance. So that's why the moon is falling around the Earth. However, it's not falling into the Earth because of its distance that's far away. The Earth's gravity is not pulling on it at 9.8 meters per second squared, because this r is much larger for the moon than for you or me, because we are standing right on the Earth's surface. Okay, so next, let's look at these these four pictures. These are all examples of things moving in circular paths. And again, you're asking yourself, what keeps the objects from moving in a straight line? So that's always what you ask yourself when you have a centripetal force problem, because you have to identify what that force is before you can go on with the problem. We've already talked a little bit about some of these. So the ball and the string, this is like the finished fling. It's like a centripetal, or a centrifuge. This is an example of a satellite, or the moon going around the Earth, or the sun going around, or the Earth going around the sun. And this is an example of a car on a curve. So let's talk about the ball first. We've talked about this one a bit already, and we've established that to keep this ball moving in a circular path, there has to be a tension in the string. So since we know that this is the centripetal force equation, then the tension in the string will be equal to 1/2 mv squared over r. That is true whenever this thing is moving in a horizontal circle. So I don't have that written on this slide, but that's key, that this is a circle that is horizontal to the ground. It's tipped up a little bit just so you can see it a little bit better in this graphic, but imagine this as being completely horizontal to the ground. Okay, the next one we'll look at will be this one. So we have a satellite. So here we have a satellite, and the force that keeps this satellite moving around is the gravitational field of the Earth. So the Earth's gravitational field is what keeps this satellite from moving straight out and going off into outer space. It's being pulled toward the Earth, and it's accelerating straight toward the center of the Earth. So this is the formula for Newton's law of universal gravitation. And we know that this thing is moving in a circular or near circular path. So we know there's a centripetal force on it. So we can take this formula and we can set these two equal to one another and solve for some other part of this problem. Pardon me. So this one's a little bit more sophisticated, but there's one problem on what I've assigned where you have to look at this kind of an idea. This is not rocket science, okay? We know what all these things are. This is a tangential velocity. That's a radial distance between center of masses. That's the mass of the rotating body. So this is the mass of the satellite in this case. So this would be the mass of the satellite right here. And in this case, the notation is inconsistent. So this m would correspond to m2 in this picture, and m1 would correspond to the Earth in this picture. Next one, so this is the finished fling, and so this is one I want you to think about for a minute. You've probably all been on this ride, and it spins around, and when you spin around on it, your back is being pressed up against the edge of the wall, the spinning wall. So let's assume that you're this little guy right here, okay, the one I'm kind of touching with my cursor. let's imagine this is the force diagram for him, and this is his back against the wall. The only reason he's not moving in a straight line is because he's got the wall pushing against his back. It's a terrible thought, but let's imagine that he's standing there and his spot is at the doorway and the door flies open. Well, this sad little sack is going to go flying out the door because there's not going to be a normal force to keep him in a circular path any longer. He's going to move in a straight line right there, and he's going to go flying off in a straight line. Everybody else keeps spinning, but he'll fly through the door and go in a straight line. So anyhow, this is important that in this case, that it's the normal force that is keeping these people in their circular path. This is one that's a little bit more complicated. We'll do this one when we get back because it's pretty easy to figure out what that normal force is. I mean, it's not the weight, but we can figure out how much friction there has to be. This is kind of a fun little problem, but we'll come back to that one. Then this last one. Okay, there's quite a bit on this one in the assignment that I'm going to have you do today, where you look at cars that are on unbanked or flat curves, or cars that are on banked curves. So you don't have to solve any problems for cars on banked curves, but I want you to look at the geometry of them. So in this case, a car that's moving around a curve like this, in order to stay, imagine what would happen if this was a very icy day and you went driving, here you are, the cursor is the car, you went driving like this, you hit what you thought was a good road, but it's really icy, and you're not going to do any curving at all. Instead, your car's going to go straight ahead. So the thing that keeps your car curving around the circular path is the friction between the tires and the road. And it's actually a friction force that points in toward the center of rotation. So in this picture, the centripetal force would be right along where my cursor is, along that radial path, and so that's going to be the friction force. So in this case, we could set the friction force equal to mv squared over r and solve for some important stuff. So thanks for making your way through this. Now go ahead and get on to the rest of the resources that I provided for you on Canvas and do the CK12 assignment that's there. You're doing great. Keep it up.